Good afternoon, everyone. My name is Brúnó Bánk Balázs, and my PhD working title is Novel Methods to Optimize Cardiac Catheterization. I am a PhD student and a medical doctor interested in interventional cardiology. My vision is to enhance the safety of the cardiac catheterization laboratory team by reducing occupational hazards. Therefore, my mission is to provide forward-looking and novel scientific results in occupational radiation safety. To achieve this mission, currently I have two projects underway. The first one is investigating the risk of radiation exposure for different personnel during fluoroscopy-guided cardiovascular procedures, and we are conducting a systematic review and meta-analysis to answer this question. The numbers of percutaneous procedures to treat cardiovascular diseases has rapidly expanded in the last few decades, and those performing these types of procedures have significantly higher risk to develop several health problems connected to ionizing radiation. The association with cataracts is well documented, but there are also growing concerns for radiation-induced malignancies with reports signaling predominantly left-sided brain cancer among interventionists. As you can see on the figure, the key staff members' positions are fixed in the catheterization laboratory. The first and the secondary operator standing on the right side of the patient, the anesthesiologist and the interventional imaging specialist usually stand at the head. And we believe this position can determine the exposure risk, and with this study our aim is to examine the radiation hazards between different personnel in the catheterization laboratory and identify occupation in need of a higher level of radiation protection. So the question is, which personnel have the highest radiation risk during cardiovascular procedure? And in our framework we are comparing the radiation of ancillary staff members to the primary catheter operator. And our hypothesis is that the ancillary staff members standing at the head have higher radiation exposure than the primary operator, and those standing in the secondary position have lower radiation exposure. During our selection process, we involved 23 full texts, and in our analysis we are collecting articles comparing dosimetric radiation data per procedure data between staff members, and we were able to involve more than 7,000 measurements in this big plot in 3 different subgroups. For better visualization, I will cut this plot in 2. And we also have to notice that between these studies, they use dosimetry on different body parts, sometimes covered by the lead apron, and there can be 104 differences between these per procedure radiation data due to the influence of procedure type, complexity, the operator radiation awareness, and so on. So we decided to do a relative comparison and use ratio of means as a summary statistics. And in our first subgroup, what you can see above, we are comparing the radiation of the ancillary staff members standing at the head position without any additional shielding compared to the shielded primary operator. And the ratio of means is 1.77, which means that these workers standing at the head receive 77% more radiation than the shielded primary operator. In the analysis you can see a clear tendency, and they receive almost twice as much radiation, so it's clinically very significant, and it did not reach the statistical significance yet due to low numbers. In our second subgroup, which you see above, we are comparing the radiation of the staff members standing at the head when they use additional shielding compared to the shielded primary operator. And in this case, the ratio of mean was 0.26, which means if they are use an additional shield, they receive the quarter of the radiation of the primary operator. And we have to notice that there is a significant difference between the confidence intervals of these two subgroups. So the application of an additional shield at the head position creates a very relevant difference and decrease in the radiation received by these workers. This is our third subgroup, where we are comparing the ancillary staff members in the secondary position to the primary catheter operator, and with a ROM of 0.33, we can say that they received the third of the primary operator's radiation. So in conclusion, it is important that every catheterization laboratory where our workers at the head position, there have to be any form of additional shielding solution for them to protect them. Yes. And we are behind with the risk of bias, but after then the grade assessment, we will start to write the manuscript. My second project is evaluating various types of radioprotective equipment in the catheterization laboratory, or the Everett study, and this will be a cross-sectional observational study conducted with imaging phantoms. As I mentioned earlier, there are concerns for cataracts and brain cancer induction, and we are knowing these risks, but worker safety in the cath lab often remains inadequate. Every personnel stepping into the cath lab legally obliged to wear radiation protection apron and thyroid collar, but we have to notice that the body parts not covered by the lead apron is also important, and physicians' heads are susceptible to 20 or 10 times higher radiation than the covered body parts. Therefore, we would like to evaluate in this study various types of radioprotective solution for the protection of the head organs in the cardiac catheterization laboratory. And as you can see on the figure, the radiation is usually coming from below, even from the radiation source or from the patient as a scatter radiation. So it is an important question if you are using a leaded field shield which is open at the bottom. Maybe it can be susceptible for higher brain radiation compared to these extended collars, where is a shield in the way of the radiation coming from below. We don't know exactly how these things and these specific devices influence the radiation of these organs. So this is what we'd like to know, and the question is which personal radioprotective device most effectively reduces radiation exposure of head organs in anthropomorphic imaging phantoms. And we will build a model, and we will make dosimetric measurements using different types of these devices. And it is important because if we apply the most effective protection for the workers, it can reduce the hazard of chronic radiation exposure. So to summarize my work, we are almost finished with the first project, which highlighted who are the workers most in danger of radiation exposure, and our second project will bring clarification on which are the most effective ways to protect them. I would like to close with the word of Marie Curie: nothing in life is to be feared, it is only to be understood. Thank you for your attention.
Thank you very much. Questions from the audience?
I would like to ask how much is this phantom model you use for your second project?
We would like to use two phantoms, one in the position of the patient, which we will give with the fluoroscopic radiation, and we will put one doll or phantom model in the position of the primary catheter operator, and we will place dosimeters on the operator model, and we are hoping that we will be able to access anthropomorphic model where you can put a dosimeter inside of the head. So this would be the best solution to measure the brain radiation or model the measurement of the brain radiation.
Okay, thanks.
Thank you
very much for your nice presentation.